Hello everyone, my name is Francesco. I work at the Department of Chemical Sciences of the University of Padua. So I'm a chemist by education, but I always work as a theoretician. So what I would like to do during this course, in these 3 lectures, is to construct, from really the basics, a thermodynamic theory of chemical reaction networks, of chemical processes. So if you're wondering why dealing with the thermodynamics of chemical reaction networks in a school about energy, information, and evolution in biology, well, there are different ways we can answer that question. One way is by noticing that many processes, the underlying mechanism of many processes in biology is based on chemical reactions, right? Many reactions sharing a lot of intermediates, a lot of species. And thanks to them, you can really create a lot of complex behaviors. For example, you can organize a species in space. You can create patterns, waves. You can control the motion of molecular motors, so to transport a load from one side of the cell to another. You can process information, and then you can also convert a form of energy, saying something stored into nutrients, into something else, like ATP. All right? And all of these processes, they are based on chemical reaction, and also they operate out of equilibrium, meaning that they dissipate energy. All right? To create this complex behavior, we need to spend energy. And so if you start wondering, how much energy does it cost? What's the efficiency of such a process? What's the performance? Can we improve it in some way? Well, to answer those kinds of questions, you need to build a theory which is able to quantify the energetics, so a thermodynamic theory. And of course, a lot of people work on that, and the history of, if you want, chemical thermodynamics is as old as thermodynamics itself. So it started really in the 19th century, where there were the first results about chemical thermodynamics, the notion of chemical equilibrium, right? And when a reaction is spontaneous or not. And then at the beginning of the 20th century, people started moving forward, away from an equilibrium description towards something that was out of equilibrium. But at the beginning, they were really trying to obtain a theory that was closed in terms of thermodynamic quantities. And they were able to characterize the energetics only close to equilibrium. But with further developments, the idea was to they started thinking about connecting a thermodynamic description on a dynamical one with a relationship that we are gonna construct also in this course, which is known nowadays as local detail balance, or someday someone can call it also a generalized detail balance. And then, in the second half of the 20th century, also mathematicians came into play, starting characterizing these complex set of reactions in terms of networks, okay? And to characterize them with an object called stoichiometric matrix that we are gonna use as well. Of course, mathematicians were more interested, if you want, in the dynamics of these networks, when they can create complex dynamics and when they just relax towards a steady state. So the existence of functions telling you which kind of behavior we will observe given network of reaction. And also the notion of cycles, so sequence of reactions that maybe create some complex result, was developed around that time. And it's only at the beginning of the 21st century that people started grabbing and using all these tools, the stoichiometry and the notion of cycles, in the framework of chemical thermodynamics. All right. What I would like to teach you, or try to teach you in these classes, is actually a contribution coming, say, from 2014, by the work that has been done in the group of Massimiliano. And the way I structured the course is in 3 classes, okay? But the first one is, spoiler. The first one is really about the basics. So the basics of thermodynamics and how to formulate it for chemical reactions, all right? And just in the class of this afternoon, I will introduce this notion of the stoichiometric matrix in a way, and the properties we can extract from the stoichiometric matrix. And in the class of tomorrow, we will use these properties to formulate thermodynamics in a way that really shows which are the mechanisms maintaining reactions out of equilibrium. If you want to use a thermodynamic language, which are the forces that are keeping your, which are preventing your system from relaxing towards equilibrium, all right? And I just want to mention that this is not just the result of my personal work, because many people really worked in the group of Massimiliano over the years, and the understanding I'm trying to give you about these problems is the collective result of the effort of many, many people. We are trying really to sum up everything in a sort of review, but this is really the joint effort of many people, and the understanding, again, that I'm trying to transmit to you during these classes is really the work of many people who passed who spent a couple of years at least there, all right? Okay, but before we start diving in, okay, let me just give you a sort of flavor of the reason why topology is important to understand the behavior of these chemical systems. So imagine you have a system which is represented by the gray box, all right? And this system is coupled to what I'm going to call a thermal reservoir. You can think of it, if you're not familiar with the term, as a big system with a fixed temperature. And because of the exchange of energy with our system, with the molecule A inside, our system will eventually thermalize, so it will reach the same temperature of this thermal reservoir, okay? And the same can happen if we exchange molecules, the molecule A, with a particle reservoir, a molecular reservoir, okay? Again, you can think of it as a big system with a fixed chemical potential. And because of the exchanges, the chemical potential of the species A inside the system will eventually be the same as the chemical potential in the reservoir, okay? So we can equilibrate with the thermal reservoir and with the molecular reservoir. So we say the system is detailed balanced, okay? Now imagine that we couple the system now with two thermal reservoirs at different temperature. And eventually you will get a heat flux from the hot reservoir to the cold reservoir, right? This is something that you can experience every day. If you put something hot in contact with something cold, you will see a heat flux, right? The point is that the same happens if you connect your system with two particle reservoirs, two molecular reservoirs, if you will. One at higher chemical potential, the other at lower chemical potential. And the result will be a flux of molecules through the system from the reservoir at higher chemical potential to the reservoir at lower chemical potential, okay? Like from high temperature to low temperature, from high chemical potential to low chemical potential. And we say that we broke the condition of detailed balance because we are out of equilibrium. We get these fluxes of energy and molecules. Now, let's complicate the system a little bit. You have two kinds of molecules inside, A and B, and you couple your system with a reservoir of molecule A and a reservoir of molecule B. The system can still equilibrate with both, okay? Inside the system, eventually, you reach a condition where the chemical potential of A is the same as the chemical potential of the reservoir, the same for B. Eventually, the chemical potential inside B will be the same as the reservoir. So again, we have a detailed balance system. We're going to elaborate on the meaning of these terms during the course. Now, say you have a reaction converting A into B, and we are still coupling the system with a reservoir of molecules A and the reservoirs of molecules B. Now, you can end up having a flux of molecules from the two reservoirs via the system through the chemical reaction. And even if the kind of coupling with the environment is the same, because of the existence of this reaction inside, we stay out of equilibrium and we transfer molecules from one reservoir to another. That's a good question. That's a question we're going to answer during the course. and it's even more complicated if you have a different reaction. Sure, but you can still, basically the idea is that you inject a molecule of A is interconverted into B, and B leaves the system. And because of the different chemical potentials of the two reservoirs, you are pushing the reaction towards one direction instead of the other. But I mean, that's not, it might be not obvious, and we are gonna explaining why that's not obvious during these 3 classes. And maybe even less obvious is when the reaction is slightly different. So instead of converting A into B, you get B plus C. This system is again detail balanced. It will reach an equilibrium, even if, again, the reaction is not so different from the previous one. And if this is not clear to you, I'm very happy, because we are going to explain why this is happening here. This is, if you want, the point to understand the topology, so the stoichiometry of these reactions, to understand whether or not the coupling with the environment will create forces keeping the system out of equilibrium. Okay? And if this is not clear, for systems that have 1 or 2 kind of molecules and 1 reaction, imagine you're dealing with a network of reactions, like your metabolism. How difficult can it be to understand whether the system is actually out of equilibrium, or if the system is just, relaxing towards an equilibrium state, right? And the point is really to understand, when we have a complex network of reactions, which are the tools that we need to understand if the system has some kind of forces maintaining the system out of equilibrium, if the system is relaxing towards equilibrium, or if something else is happening. All right? So this is basically kind of the program. I will use both slides, then Blackboard. Just once a day, I'll use the Blackboard too. Again, if you have questions, just feel free to ask me. And okay, great. So I'll start setting down the basics, like notational and etc., 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 and then we can move to the thermodynamics, right? So first part, really basics of the dynamics and the thermodynamics of these networks of reactions. Okay, so we are going to assume that we are dealing with systems like the one represented here, where you have a lot of species, okay, which are labeled I, and you have the set of species. The system is homogeneous, so we are assuming that all species quickly equilibrate in space, so we are not going to care about whether they are spatially distributed or not. Everything is homogeneous here. We assume they are diluted, so we have chemical species mixed together with something that is much more abundant, a solvent, if you will, which is also fixing temperature and volume of our system. Okay? Sure, we can share them. There's no problem about that.
Yeah, we will create a folder where we will put the PDFs of the different presentations.
Okay, so we have species, and then we have an additional species, a solvent. The solvent will not be involved in the reactions, all right? It's just there to fix the temperature and the volume of the system. But if you want, in cells, you have water, which is much more abundant than everything else, all right? And we are going to assume that our system is open, so some species are going to be exchanged with the environment, all right? And these flasks here represent whatever we don't know about the environment, all right? And if you look at this example, here you have the actual set of reactions that are gonna be always reversible, all right? For every reaction taking you from some set of species to another, we are gonna assume that there is always the backward reaction, all right? But in all the drawings, you have only the forward reactions represented there. It's just for clarity, because in drawing also the backward arrow is going to be a mess. So you're going to see just forward arrows, but all reactions are reversible. Okay? And you can think about this model, this example that we are going to use all over the course, as a sort of minimal metabolism. Okay? You can imagine that you have an enzyme binding a molecule F, a fuel molecule, if you will. You get a complex. You interconvert the fuel into a waste, and then you release the waste. But the complex between the enzyme and the fuel can bind also a substrate. You can think of the substrate as ADP. And then then the new complex can release another molecule, a product. You can think of it as ATP, and then you get back to the complex with the waste. So in a way, you can think of it as a process interconverting fuel into waste, nutrients into CO2, if you want, to power up the interconversion of a low energy molecule, a substrate, ADP, whatever, into a product, a high energy molecule, ATP. Okay? And just to clarify, I'm going to use rho as the label of the reactions, and R is going to be the set of all reactions, right? Sorry, it stands for chemical reaction networks. Sorry, forgot about that. Yeah, you're going to see it quite a lot. Okay, dynamics, all right? So we are going to assume that the species are highly abundant, okay? So that we don't care about the fluctuations of each reaction. And we can safely describe the dynamics in terms of a deterministic rate equation for the concentration Z of the chemical species. So Z is going to be a vector of the concentrations of all species but the solvent. The solvent is not involved in the chemical reactions, so the concentration of the solvent doesn't change in time.
If the solvent is involved in a reaction, does this cause any particular problem?
You need
ATP exfoliation or something, you get some water in and out. So it doesn't change the concentration of the solvent?
no. You can treat it, if you want, as a different species. The only no, there's no big problem as long as you don't have interactions. If you have interactions, I think the dynamics might become a little bit more complicated. But no, in general, it doesn't have. It's not a problem. Yes. You can think of it as like, yes, if you want, there's a reservoir of water, and it's providing water molecules every time they are needed for a reaction.
So, because I guess, so you have the total concentration is constant or not necessarily?
It doesn't have to be. For what I'm going to explain, I'm assuming it is of the solvent, but it doesn't have to be in general. I'm just like, okay.
Sorry, the total concentration of non-solvent molecules
Is not constant.
not
No, that's not constant in general, especially if you have like biomolecular reactions, right? So like imagine you have two species A and B going into C. The sum of the three in terms of concentration, that's not constant. No, okay. Okay. So, and the dynamics of these concentrations is going to follow a rate equation like this one. Okay, and now I'm going to explain you all the terms of this equation. All right. Yeah, it's a no. Okay, let me stress this. So there are. So I'm making a bunch of assumptions that are not necessary, but we're dealing with deterministic rate equations because we assume the concentrations are large enough that single reactions don't change the concentrations enough to create fluctuations in the concentration. But you can transfer everything that I'm going to try to teach you today to also a stochastic process. You can extend it to a system where the concentration of the solvent changes in time. It's just that I'm trying to set the simplest possible setup to like stress the role of the network of reactions instead of all the other details that can be transferred again, but they are unnecessary to the point of determining these thermodynamic forces. Okay? So, first term in the rate equation, S. I already mentioned before that S is a matrix. We call it a stoichiometric matrix. So imagine that do you see the equation that is written here? Okay. So imagine you can write every reaction as a combination of species, Zi, weighted with some coefficients, and those coefficients are the stoichiometric coefficients, right? You have for each reaction rho, the stoichiometric coefficient I of the species I, okay? And on the right-hand side, you have a combination of species, Zi, weighted with the stoichiometric coefficients of the backward reaction. I use minus rho for the backward reaction of reaction rho, okay? And for each reaction, you can collect those coefficients into vectors. So you have a vector of stoichiometric coefficients for each reaction. The entries correspond to the different species. And you have a vector of stoichiometric coefficients for the forward reaction. The difference between the two gives you the net variation in terms of number of molecules for each species along a certain reaction rho. Let me give you an example. Let's look at the example we have here, and we look at reaction 3. So reaction 3 converts EW, the complex of enzyme and waste, into E plus W. So if we look to the column of the stoichiometric matrix corresponding to reaction 3, we have -1 for EW, right? It plays the role of the reactant. And then we have +1 and +1 for W and E. The order is not important. We could have called the opposite reaction as the forward one, so E plus W to EW. And we have to flip the sign of these entries, but it doesn't matter. That's totally arbitrary. Okay? Again, no, it doesn't have to be 1 of -1. Because if you have something like, do you see here? 2A into B, you're going to get -2 for A plus 1 for B. So imagine you have one reaction. So your stoichiometric matrix is one column, one entry for A, one entry for B, -2 plus 1. If you think of this process as the forward reaction and that one as the backward reaction, but you can flip it. You can consider this is as the forward process and this as the backward process, and then you have +2 -1. Doesn't matter. All right? Which current? I'm going to tell you about that. So this is just the first term. Again, let me stress it again. You have a matrix. Each row corresponds to a species. Each column corresponds to a reaction. And so each entry tells you the net variation in terms of number of molecules for a species in a specific reaction. Second term, this is a current vector. So if you want, is the rate is the vector which has entries for every reaction, and each entry of that vector is the current, the rate at which each reaction occurs. And it's given in terms of the difference between the forward flux and the backward flux. So for each reaction, you have a flux going in one direction, and then you have a flux going in the backward direction, telling you how many times the forward reaction occurs and how many times the backward reaction occurs. The difference gives you the net current of the reaction, this J rho, okay? And the vector J collects all the currents for all reactions. For simplicity, we are going to assume that we are dealing with ideal systems, okay? No interactions except for the chemical reactions. So we can express the fluxes of the reactions in terms of mass action law. We have a kinetic constant, and then the the concentrations of the different species to the power of their stoichiometric coefficients. So every time you see a vector to a power of another vector, I mean the product over the entries, in that case of Zi rho I. Okay? Again, this is not necessary. We can deal with non-ideal systems, okay, where we have interactions, and so the expression of the fluxes is going to be different, but that doesn't matter. This is for simplicity. There was a question? So ideal dilute solutions. In that case, you get mass action law. For non-ideal, non-diluted systems, no. You have a different rate equation. It doesn't matter. It's just that here for it's simpler to deal with that kind of system. But you can extend everything beyond ideal, diluted, even non-homogeneous systems. Okay. That one? I'm just saying that every time in the slides you see a vector, z, for example, to the power of another vector, you take like the product of each entry. So you take each entry, zi, to the power of the corresponding entry of the second vector. And then you multiply everything. So if I'm using the example of concentrations and stoichiometric coefficients, but if you had just a vector w, v and a vector w, you would have something like product over I, vi, wi. Just two vectors. It's just to simplify the notation. It's written also over here. Last term. No, sorry, yes. I want to stress that this is just for ideal dilute solutions. Okay, the last term accounts for the exchanges with the environment. Okay? For example, here, you have all the exchanges with the environment for the species F, W, P, and S. So if you look at this exchange current, for the example, you have null entries for the species that are not exchanged with the environment, like E, EF, EFS, EW. And then you have some terms for the species F, W, S, and P. Because those are the species that we are assuming are exchanged with the environment for the specific example we are dealing with. Okay, now how to think about those exchange currents? There are different ways to think about that, but we are gonna assume that the environment is controlling the concentrations of the species that are exchanged. Say the concentrations must be equal to a certain value pi I. Okay, we are thinking that the environment is controlling those concentrations, like the abundance of glucose. Okay, like the pressure of CO2, things like that. All right. So the currents, the exchange currents, become the processes balancing the variation in the concentrations due to the chemical reactions. So the reactions are changing the concentrations, like every time the first reaction occurs, F is consumed. But there are processes, we don't know anything about them, but there are processes balancing that variation and replenishing F every time F is consumed. Okay? So in a way, we are defining those exchange currents as a difference between the concentrations the environment is imposing with respect to the variation due to the chemical reactions. Is that clear? I don't want to lose you here. Yes? Imagine that in your environment, for reasons, yes, it's something predefined. Imagine the level of the CO2 is changing for, I don't know, atmospheric reasons. Then the environment is imposing, if you want, a certain protocol about the pressure of the CO2. And that's the way you should think about pi. Come again? S is just the row of the stoichiometric matrix corresponding to the species I. I'm just rewriting, I'm specializing that equation for a single species. I forgot to say that, sorry about that. All right, this is the way we're gonna think about it, okay? But it's not necessary, meaning that I could be whatever. It could represent a constant injection or extraction of species, all right? So you have a constant intake or outtake of species, or you could have a constant intake and an outtake of species which is proportional to their concentration. Like you have these reactors, you push in species at a constant rate, but you extract them at a rate which is proportional to the concentration. It doesn't change what we are gonna do, okay? The point is that, again, dealing with this control on the concentrations is just simpler for our purposes, okay? So we are gonna assume, if you wanna use like a classical stat-mech approach, we are gonna assume that we have particle reservoirs that we can call chemostats, controlling the concentrations of those species. Again, you can think of it again, you have like a sort of environment where glucose is kind of constant. The pressure of oxygen or CO2 in the environment is kind of constant. And you can think of those environments as reservoirs of glucose, oxygen, and CO2, okay? And I'm gonna use the word chemostatic exchange as synonyms, okay? So either I'm gonna say that the environment is chemostatic a species, or the system is exchanging a species. It means the same, okay? I'm not doing that on purpose to confuse you. It's just that I'm used to those words as synonyms, so I'm gonna use them as synonyms as well. I hope it's fine. Okay. Okay, so this is the dynamical system we are dealing with. Let me stress it again. Z is the vector of the concentrations of all the species. The product between S and J gives us the variation to the concentrations due to the chemical reactions. If you want, again, J is the rate of the reactions, and S encodes the variation in terms of number of molecules every time a reaction occurs. I tells you the variation to the concentrations, or the known variation to the concentrations, due to the environment. Okay? Hope that is clear, because everything else is going to be built on top of that dynamical system. Yes, people saying yes, so I'm going to believe that. So, dynamics, there are special points in the concentration space. They are called steady state. So concentrations such that if the system has that, if the species have that concentrations, it's a stable point. The concentration will not change in time. So the general expression for a steady state is this one. So the concentration, the term on the left-hand side of the equation, we set it equal to 0. And so the steady state condition is such that the variation to the concentrations are always exactly balanced by the exchanges with the environment. And if we have exchanges, we say that the system has a broken detailed balance condition. If we instead we are in a special case where the currents of all reactions, all of them, are equal to 0, meaning that if you remember the expression for the currents, they are given by the difference between the forward flux and the backward flux. So if the currents are equal to 0, it means that each flux is equal to the flux of the, each forward flux is equal to the backward flux, right, of the corresponding reaction. So they balance each other, exactly. And since this must be true for all reactions, we say that we have a detailed balance condition. Okay, so we balance all reactions. Yes, please. Yes.
So you said that even if a reaction is indicated with an arrow, the reverse
yes.
reaction exists
Yes.
in the system.
And that's we cannot escape that.
That's okay. But within the CRN approach, you can take the elementary rate constants to have any values.
Yes.
Or you can take those that are derived from a potential, meaning that they always support some detailed balance equilibrium.
Yes. Yes.
Is that the assumption that you will make here everywhere?
Okay, let me clarify about that. So when we deal with systems in which we assume that the concentrations F and S, W and P are constant, right? We can sort of absorb that concentrations inside the kinetic constants. We're not doing that here. We are accounting for all species. So the kinetic constants always satisfy a detailed balance condition.
Good. So AKA there's an assumption that there's a microscopic reversibility under
Yes, yes. The kinetic constants, so if you're thinking about the condition that along each cycle, the product of the forward kinetic constants must be equal to the product of the backward ones, that's always true. Because the irreversibility, if you want, comes from controlling those species, because we are not absorbing the concentration of those species in the kinetic constants.
Yeah, maybe the assumption that you have not stated explicitly is the one of elementarity.
Ah, right. That was important. All reactions are but okay, I'm gonna tell. Okay, never mind. All reactions are elementary, meaning that we are not hiding anything under the carpet. Everything is explicit. We don't, coarse grain intermediates. Everything is elementary, so every reaction as we account for all species or reactions, etc., etc., etc. Yes, question.
You already mentioned what is pi?
Pi is like is the concentration of species I imposed by the environment. So imagine like again, glucose is yes, it's like a protocol. The concentration of species I must follow because the environment is telling you to do so. It's the pressure of oxygen, is the concentration of glucose in your batch. Again? It's not preferred because it's like really the environment telling you which concentration of that species you have. Like you prepare your you want to grow cells on how do I call it? On certain quantity of glucose. You prepare your batch, you put a certain amount of glucose, and then you put your cells in. The concentration of glucose is gonna be it's gonna stay constant for like a certain time scale, and so we are assuming that along that time scale, the concentration is constant and it's imposed by the environment. It's not preferred because like also the pressure of oxygen, imagine it changes, then the environment is telling you that. Okay. Yes. So we have these two kind of like steady states, and just to be sure, because I forgot to say that before, when we have when the system is detail balanced, okay, all reactions are balanced, so all currents are equal to 0, which means if you look at that expression, all currents are equal to 0, the first term is 0, so also the exchange current must be 0. So there are systems that, despite being open, right, can reach an equilibrium condition, and at equilibrium, the exchanges with the environment stop because we don't need to balance the concentrations anymore, because the reactions stop to occur. Okay. Now, the point now is to construct a thermodynamic theory, all right? And the way we're going to construct it is by building it on top of the dynamics. The idea that we're going to follow is to find a correspondence between the dynamics and the thermodynamics. And then we are going to use the dynamics to follow how the thermodynamics changes in time, like thermodynamic quantities, say heat, say free energy, okay? And to do so, I'm going to work on the blackboard, okay? We are going to construct a condition known as local detail balance, which relates the dynamics and the thermodynamics, okay? I'm gonna leave the projector on because I was told that it takes a lot of time to turn it off and turn it on again. So if the light is fine,
But maybe we should try to
you can.
on those lights so that you can use more of the blackboard.
Which lights? Which zone? Ah, okay.
And then everything between the two lines is fine.
Okay. This is complicated. Okay. So the point, again, is to find the correspondence between dynamics and thermodynamics, okay? Okay, let me start with showing you that we can find a correspondence between, first point, is a correspondence between the kinetic constants and the equilibrium concentrations. Okay? So if you remember the expression of, wait, sorry, I forgot an important point. So why we can create a correspondence between dynamics and thermodynamics? The reason is that when we deal with a closed system, okay, a chemical system will relax to an equilibrium state. Okay, so sooner or later, we are going to get to an equilibrium state. And there, we know that we can write down thermodynamic quantities, because that was done in the 19th century. So we can rely on that and construct thermodynamic quantities. We are going to find the condition for the equilibrium state from the dynamics, and then we are going to relate the two. So we are going to assume that our system is closed. So sooner or later, we will get to an equilibrium state, because we are not providing energy to the system, right? We're not exchanging energy, molecules, with the system. So sooner or later, whether we like it or not, we're going to get to an equilibrium state. And now we relate dynamics and thermodynamics because of that, yes.
For dynamics, it doesn't matter how far we are initially from the equilibrium.
Yes. And we're going to see that it doesn't matter also for the thermodynamics. Sooner or later, we're going to get to the equilibrium state. So the expression for the fluxes in terms of mass action kinetics was something like this, right? So kinetic constants, concentrations to the power of their stoichiometric coefficient. This is R of rho. Sorry. Now, at equilibrium, from what we said before, this is exactly equal to K minus rho Z equilibrium to the power of the stoichiometric coefficients of the backward reaction. Okay? This implies
Don't you want the minuses switched in the V's because it's the input stoichiometry to each reaction, not the output?
don't I want the
K rho Z to the V minus rho?
yes, there's a minus here and there's a minus here. So I'm just using rho for the forward reaction and minus rho for the backward one.
And V minus rho, isn't that the input to the
Backward reaction. So you have okay. No. Okay. So if you want, this is the reaction going from left to right, K plus K rho, and then you have the backward one, K minus rho. And here you have the combination of species, sum over species, mu I rho Zi. And here you have sum over the species, mu I minus rho Zi.
I guess the confusion comes from when you write S in terms of mu. If you write the stoichiometric matrix in terms of the mu,
Yes, and
you're right, it's too easy to say.
I mean, I could say plus rho. Okay. Okay, we can rearrange this equation to get K rho over K minus rho equal to Z equilibrium nu minus rho, nu plus rho. And this is the column of the stoichiometric matrix for reaction rho. So the first point for us, now let me rewrite it with just a logarithm and RT, just because then we're going to connect the dynamics and thermodynamics. So RT log of K rho over K minus rho is equal to RT log of Z equilibrium scalar product with S rho, the column of the stoichiometric matrix. So every time I write the log of a vector times another vector, I mean the sum over all contribution. Okay, this is the first point. So we have a connection between the kinetic constants and the equilibrium concentrations. Now the second point will be to create a correspondence between the equilibrium concentrations and some thermodynamic quantity, all right? So imagine we are at equilibrium, all right? We know how to write, okay, maybe most of you have a physics background, right? For the others, just believe me, I guess. We know how to write a free energy of our equilibrium state, which depends on the concentrations of the species involved in the reaction. And then we have also the concentration of the solvent. And this is given by sum over all species, chemical potential of species I, which again is a function of the equilibrium concentrations and the concentration of the solvent, concentration of species I, plus chemical potential of the solvent, concentration of all species at equilibrium, concentration of the solvent, times concentration of the solvent. And for ideal dilute solutions, we know the expression of the chemical potentials of solvent and species, which is the following. Z equilibrium, Z0. We have a standard contribution, which is, if you want, a sort of the internal free energy of the species I, plus RT log of Zi over sum over J, all species, equilibrium, equilibrium, Z0. Same for the solvent. We have a standard contribution. This is 0, solvent plus RT log Z0. What multiplies? No, it's equilibrium. All right. Okay. If you're not familiar with this, just say, just let's assume that this is the expression of the chemical potentials in ideal mixtures. Okay. What we didn't use yet is that the solvent is much more abundant. Okay. So in the chemical potential, you see that the log term depends on the concentration of the species with respect to the total concentrations. We have the sum over all the reacting species plus the solvent. But we can approximate this because the solvent is much more abundant. So if you remember, our dynamical system, mass action law, holds for ideal dilute systems, while this is more general. So we can approximate it to a level where the solvent is, again, much more abundant, where we are dealing with dilute systems. So if, now approximation, we assume that Z0 is much more abundant than all other concentrations. Okay, so you can forget about this term, right? Because the concentration of the solvent is much more abundant than the concentration of all other species. So you're left with the log of Zi over Z0. The concentration of the solvent is constant, and we are going to absorb it in the standard chemical potential. So we get a new standard for I plus RT log of Zi. Is that clear to everybody? Just neglecting this term here. Now we want to do the same for the solvent. However, if we neglect just this, we kill the term. Okay? So that's not enough. We have to go to the next order in our approximation. And just believe me, it's given by, this is just a Taylor series, sum over Ji, Z over Z0, equilibrium. We are taking the second order in the expansion of the logarithm. All right? Now, if we plug everything into the Gibbs free energy, what we are going to get is that G of equilibrium is sum over I mu I. Now, mu I consider it as just a function of the concentration of species I. I absorb everything about the solvent inside the standard. Concentration of Zi, everything at equilibrium. And then we have the standard of the solvent times the concentration of the solvent. Let me write it here. Plus mu standard solvent concentration of the solvent. And then we have this term multiplied by RT multiply to the sum of, the concentration of the solvent, and so we get minus RT sum over all concentrations. Okay, just math. I'm just rewriting the expression of the Gibbs free energy for mixtures for just dilute solutions. Since we are going to care about variation in the Gibbs free energy in terms of due to the variation of the chemical species, the concentration of the reacting species, I'm going to drop this because that is constant. Okay, so this is the expression of the equilibrium free energy we are going to deal with. Now, just one point, and I'm going to neglect the concentration in terms of the solvent also there. But this is just, it doesn't change in time, so we're going to forget it, so we get with a simplified notation. What? Ah, yeah. Thanks, boss. So, just notice something, that if you take the derivative of G with respect to the concentration of Zi, okay, you get exactly the chemical potential as it should be. Okay? This is just, math, but the point is that you take the derivative of the log, and that cancels out with that. And then when you take the derivative of this, you get the total chemical potential. Nothing more profound than that. Okay? Now, we have an expression finally, after a lot of blah, 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 of the Gibbs free energy at equilibrium for an ideal dilute solution, all right? Which is the same kind of system we can treat with mass action law at the dynamical level, okay? So now we want to understand something more about how to create a correspondence between the equilibrium concentrations, and some specific thermodynamic quantities, because spoiler, we're gonna relate those with the kinetic constants via the equilibrium concentrations. How to do that? Well, again, equilibrium thermodynamics is telling us that the equilibrium is a minimum of the free energy, all right? So each variation in terms of concentrations around the equilibrium point should increase our free energy, all right? How can we express that with equations? Well, let me erase something. So we have a free energy at equilibrium. Now each variation should increase that free energy, all right? But we cannot take any variation we want. We can take variations that are consistent with the chemical reactions. And if you remember, every variation in terms of number of molecules for each chemical reaction is accounted by the column of the stoichiometric matrix. So imagine you want to perturb your equilibrium state with reaction rho. The variation will be something like, say, epsilon, so something small, times the rho column of the stoichiometric matrix. So along that reaction, this is the variation of, if I take minus G equilibrium, this is the variation of the free energy due to reaction rho. We are changing the concentrations by a factor which is proportional to the variation in terms of number of molecules along reaction rho. And since this is an equilibrium, in the limit the perturbation is small, this must be 0. Because we are in a minimum of the free energy, right? So the derivative of our free energy along perturbations that are consistent with the chemical reactions, they have to give us 0. Because we are in a minimum. This one. Yes, it's there. I'm just take. Ah, no. Okay, you say in the here. It's because when you take the derivative of the logarithm, it depends on the concentrations, right? So you derive with respect to Zi, you get the chemical potential. You derive the chemical potential with respect to the concentrations, you get plus RT. And from here you get minus RT. Sorry, that's the step that I skipped. Maybe I should have. Okay, now remember that the variation of the Gibbs free energy with respect to the concentration Zi is the chemical potential. So that expression here is actually equivalent to sum over I mu I Z equilibrium SI rho. Right? The sum over all species, I take the chemical potential of those species times the element of the stoichiometric matrix for species I, reaction rho. So, because the derivative of G with respect to the with respect to the concentrations is the chemical potential, and we do that for all species, and we get that. Is that clear? So, in a vector notation, we would have something mu now is the vector of all chemical potentials for all species at equilibrium, scalar product of the column of the stoichiometric matrix rho equal to 0. Okay, remember this because this is something we are going to use also tomorrow. Okay? Just a sec. This is also known as, if you want, the delta G of reaction rho at equilibrium. And probably from the basics of thermodynamics, most of you know that the delta G of a reaction is equal to 0 at equilibrium. We are not inventing anything here. We are just rewriting things that are basic thermodynamics with a notation that it's going to be useful for later. Yes? Yeah. This is. Do you want me to do it? Or no. Yeah. I'm just. This is equivalent to this. It's just a rewriting, if you want. And the reason why they are equivalent is because the derivative of. This is just taking the derivative of G in like the direction of S rho. Okay. Now, if you remember what I just erased. So this is the. No, sorry. Okay, let me rewrite it. So the expression of the chemical potential, mu I, is mu I 0 RT ln Zi at equilibrium. Okay, this is what we derived just like a few minutes ago. So from that, what do we get? We get that minus the vector of the standard chemical potentials times S rho is equal to RT log Z equilibrium scalar product S rho. I'm just plugging in the expression of the chemical potential in the thermodynamic condition for equilibrium. Is that yes? So you can really think like, so from equilibrium thermodynamics, we understand that equilibrium is a minimum of free energy, meaning that whatever our system did in the past, well, basically it was dissipating free energy because we are dealing with a closed system. So there are no sources of free energy. So the only free energy that the system could dissipate was the free energy that it was stored inside the system. We are dissipating that free energy, we got to a minimum. Okay? Now we are taking variation of that minimum, and since that is a minimum, any variation should give you 0 if the variation is small enough. Okay, so we are just rephrasing the condition of a minimum of a free energy with a mathematical expression. Nothing more deep than that. So we are in a minimum of a free energy, because the dynamics couldn't do anything else but to dissipate the free energy that was initially stored in my system. So imagine that you are just taking reactants, you mix them together. That is a non-equilibrium state, right? You have a sort of free energy stored in the abundances of the chemicals. And the dynamics is relaxing you to an equilibrium. And from a thermodynamic point of view, that relaxation is just a dissipation of the free energy that was stored in, if you want, in the isolated chemicals, and now is dissipated until you reach your equilibrium state. And now we are looking to small perturbations to find the condition for the equilibrium in terms of chemical potentials. Okay, now you put together the two, this one and that one. So you have RT log Z equilibrium times S rho in both equations. And what you get out of it is RT log of K plus K minus, okay, I don't use the plus, equal to minus mu standard times S rho. So it's a correspondence between the kinetic constants and the standard variation of the Gibbs free energy. This is if someone of you took like classes of chemical kinetics, you see it. They always write that the ratio between the kinetic constants is equal to minus the standard delta G of the reaction. This is exactly the same. I'm not doing anything new yet. Okay? But if we think about this deeply, it means that the dynamics is not independent from the thermodynamics. They are related. Okay? So we cannot choose random kinetic constants because the kinetic constants are actually related to the energetics, to the thermodynamics. Questions about that? Yes, sorry. Delta rho G. Come again with the second part of the question? Sorry, I had to process.
Yeah, so delta rho G, you said that delta rho G is equal to mu dot S rho.
Yes.
This could change the epsilon is 1 by using.
If epsilon going to 0. No, because imagine you are expanding. So the way to think about it, you are again expanding the first term, right? So in Taylor series, the first term cancels that, and then you're left with epsilon delta G over Z I times S rho, sum over I, and then epsilon cancels epsilon. Yeah, it's finite. It's this one, exactly. Yes?
Does your delta just mean gradient in this case?
In the space of reactions, yes, if you want. It's the variation of the free energy along that reaction, evaluated, in that case, at equilibrium. Yes? Yes. Yeah, this...
So the other one is always non-zero.
No, it could be 0, because like they are measured with respect to a standard.
Okay.
So you choose the standard, and then you measure the others. So,
In this case, I can choose it to be 0 and then
well, it cannot be 0 for every species. Can't be. Well, it could be. No, okay, it could be. But then it means that all... Yeah, it could be. Sorry. But then, yes, all kinetic constants are equal between the forward and the backward reaction. So you get that this is 0, right? So the ratio between the kinetic constants of each forward and backward reaction must be 1, because the log of 1 is equal to 0. So, like, yes. from the kinetic sorry. Yes, in terms of kinetic constants, yes. But since the rates actually depend on the concentrations, depending on the concentration you have, the forward one could be faster than the backward one. Okay, I think I can move back to the slides. Yes, okay, I can move back to the slides if you don't have any questions on this. Okay, so what did we do was like, we started from the equilibrium, from the dynamical condition for equilibrium. We got out an expression relating kinetics, kinetic constants, and equilibrium concentrations. We did the same for the thermodynamics, and we related the two. Okay. Now, if you want, this is all at equilibrium. What do we have to do to go out of equilibrium? Okay, just if you want, these are the expressions of this local detail. Sorry, this is called local detail balance. I forgot to say that. That was important. Again, local detail balance meaning relating the condition between the kinetic constants, the dynamics on the left-hand side, and the thermodynamics. And if you want to express them for the example here, when we are dealing with a closed system, so you have, like, for example, K plus 1 over K minus 1. You have the difference in the standard chemical potentials of EF, E, and F. Okay? Now, how do we go out of equilibrium? Now, there's a little bit of physics here, meaning that, so what we said until now is that we know how to write the free energy of mixtures, right? Then we took the limit, if you want, for dilute solutions, but we know how to write the free energy of mixtures. And we have a dynamical system describing how the concentrations are changing in time. So you can think of every point of our dynamics, every concentration Zt, as an equilibrium mixture. And then we have the dynamics converting one equilibrium mixture into another one. So we are just extending the expression of the free energy that we have from equilibrium to a non-equilibrium state, because we have a dynamical system. Where is it? I didn't write it. Okay, the rate equation of before, telling us how the concentrations are changing in time. And that is not an arbitrary dynamical system, because we have a correspondence between the dynamics and the thermodynamics, ensuring us that a closed system will eventually reach an equilibrium state. Okay? So we didn't come up with a random dynamical system that we use to convert our concentrations. We have a constraint binding the dynamics and the thermodynamics. Now we are extending the notion of free energy from equilibrium concentrations to non-equilibrium concentrations by assuming that in a way everything but the concentrations are at equilibrium. So we know how to write the free energy of an equilibrium state, and we are using the dynamics to convert, if you want, an hypothetical equilibrium mixture into another. All right? And so by, like, if we take the local detail balance written like this, we, I should have kept the blackboard. We sum like RT log of concentrations now at each point in time times the column of the stoichiometric matrix on both sides. We can rewrite the local detail balance in this fashion, where now we have the log of the ratio of the fluxes with respect to the variation of the free energy, not the standard one, the one evaluated at each point of the dynamics. Okay? So we have a delta G evaluated at an arbitrary concentration given us by the dynamics related to the ratio of the fluxes. And if you want, we derive this here formally, but people use that also in equilibrium thermodynamics, right? When the delta G of a reaction, because of the abundances, is smaller than 0, people expect that the reaction is proceeding in the forward direction. Like, instead, if the delta G was positive, people would expect that the reaction is proceeding in the backward direction. The same is here. Imagine that the term on the right-hand side, so the delta G is negative. So the term is positive. So the forward flux must be larger than the backward flux for this equation to hold true, meaning that the current is positive. The reaction is proceeding in the forward direction. If the delta G were negative, minus delta G would be, positive, minus delta G would be negative, so the ratio must be smaller than 1. And the difference, the current, would be negative. So the reaction would proceed preferentially in the backward direction. Thanks.